Hello and welcome to another video. In this video, we will see few mathematical preliminaries that is required in control engineering. The first and foremost will be the ordinary differential equation. Why is it important to study about ordinary differential equations? Because all the physical systems that we develop, say a process control system or a mechanical system or any other electrical systems, all these systems, from the physical law governing that system, we derive some mathematical equations, and mostly it will be differential equations, which will give a relation between the input and the output. Any system can be mathematically represented. So in most cases, we use ordinary differential equations to represent the system mathematically. So generally, there are two kinds of differential equations: homogeneous differential equation and inhomogeneous differential equation. The difference between homogeneous and inhomogeneous differential equations lies in whether they contain a non-zero forcing function or a source term. Here, the function is u of t, the input. So if there is some forcing function in that equation, then it is non-homogeneous or inhomogeneous differential equation. And if there is no forcing term on the right side, if it is zero, then it is homogeneous ordinary differential equation. And the solution of that differential equation, a homogeneous differential equation, will be c into e raised to minus at, where c is nothing but the initial condition. And in case of first order inhomogeneous or non-homogeneous ordinary differential equation, we have the first part due to the initial condition, that is called the free response. And there is a second part which is due to the input that we provide, that is called forced response. Now, for a first order homogeneous differential equation or a non-homogeneous differential equation, it is easy to find the solution. But for higher order differential equations, it may be difficult to find the solution. So we transform this ordinary differential equation into the frequency domain by using any of the transform. Mostly we use Laplace transform, and then do the mathematical calculations in the frequency domain, and then transfer that back to the time domain to get the solutions easily. Now, the general form of a homogeneous differential equation is Ly equal to 0. So the right hand side is 0. And y double prime plus 3y prime minus 4y equal to 0 is an example of a homogeneous ordinary differential equation. A non-homogeneous ordinary differential equation is of the form Ly equal to fx. And the right hand side is not equal to 0. The function f of x is not equal to 0. And this is an example of non-homogeneous ordinary differential equation. Y double prime plus 3y prime minus 4y equal to x. So the right hand side, the function f of x is not equal to 0. So this are the general forms of homogeneous and non-homogeneous ordinary differential equation. The next concept that we would like to explore is the complex variables. The complex variables are important because we will be transforming the time domain into frequency domain. So there it will be, we will deal with the S-plane. So the S-plane is nothing but we will have a real axis and an imaginary axis. So any point in the S-plane can be represented by sigma plus j omega, where sigma is a real number and omega is a real number, and j square is equal to minus 1. So this j term shows the imaginary value. So imaginary axis, in imaginary axis where the point is located. Say for example, 5 plus j3. 3 is a real number, 5 is a real number, but 5 is in the real axis and 3 is in the imaginary axis due to the presence of the j. So this s is a complex variable. Now a complex function f of s is a complex valued function of s. So f of s is equal to fr sigma omega. It's a function of sigma and omega plus j into, so this is the imaginary part, fi sigma omega. It's a function of sigma and omega. An example of f of s is s square. We substitute s equal to sigma omega, sigma plus j omega whole square. And when you expand this, you will get sigma square minus omega square, which is the real part, and plus j into 2 sigma omega, where this is the imaginary part of the function f of s. A complex function f of s is said to be analytic in a given domain if f of s and all its derivatives exist in that domain. The points in the S domain where f of s is not analytical are called singular points. This is the another definition of poles of. So for example, if f of s is 1 by s plus 1, f of the function f of s is 1 by s plus 1, then the point s equal to minus 1 is a singular point or pole of this function. Another important relation is the Euler relation. So the formula is e raised to j omega t equal to cos omega t plus j sin omega t, e raised to minus j omega t equal to cos omega t minus j sin omega t. From that, after rearranging, we can also write cos omega t in terms of e raised to j omega and e raised to minus j omega. Cos omega t is equal to e raised to j omega t plus e raised to minus j omega t divided by 2, and sin omega t equal to e raised to j omega t minus e raised to minus j omega t divided by 2j. While deriving the Laplace transforms, these formulas will be helpful. Another important thing that we need to note is the standard input signals. Why is it important? We need to study about the system. If we give a known kind of input signal, say a unit in impulse input or a unit step input or a sinusoidal input, so the input is known to us, and when we give that input to the system and we analyze the output of the system, which will give a valuable information about the system dynamics or how the system relations are derived. So that is why we need to study standard inputs that is given to analyze the system. So by observing the output of the system, standard inputs, we can determine the characteristics of a system. Standard input that we will see is the unit impulse input. It is also called a Dirac delta function. So the input would look like this. It has a length of minus epsilon by 2 to epsilon by 2 in the time axis, and it has a height of 1 by epsilon. So what we do is we reduce the epsilon value to 0. We try to squeeze it. We reduce the time axis and we increase the u of t magnitude axis. So it will, when epsilon tends to 0, it will look something like this. It will have negligible time axis, but infinity magnitude axis. So that is the speciality of this function. This is one kind of input that we give to the system to analyze the system. But practically, we won't be able to give infinite value as magnitude, but still we try to give a very short time duration signal with a large magnitude to recreate the effect of the unit impulse response. So it is called a unit because the area under this will be unity. The next kind of input is unit step input, where we give a sudden change at time t equal to 0, and it has a magnitude of 1, and we maintain that value constantly as time progresses. So this is the most common type of input that we give to a system to analyze how it responds, to study about the system. Another signal is unit ramp response, unit ramp signal. So here we give a ramp as the input to the system and above the output to study about the characteristics of the system. Here u of t is equal to t. So as time progresses, the magnitude increases. The value of u of t is proportional, directly proportional to the time axis. As time axis increases, the magnitude of u of t, the signal also increases. We also give the input cos omega t or sin omega t, the sinusoidal inputs, to analyze the system. So we will get the, when we transfer it to the time domain, sorry, frequency domain, the frequency response can be analyzed and suitable information about the system can be derived. So these are also common inputs that is given to the system. Before winding up, I would like to mention a point about stability. The most common way of describing the stability of a system is bounded input, bounded output stability. So suppose you give some bounded input to the system, the output also should be bounded. So then we can say that system is stable. The system is said to be bounded input, bounded output stable if given any input u of t such that this u of t is bounded. The magnitude of the input is less than some value m, which is less than infinity. So the magnitude of the input is bounded, then the output of the system is always bounded in magnitude for all time t, such that the magnitude of I of t is less than n, which is less than infinity for all time t. Here m and n are just some finite positive real numbers. So it just means that if we give a bounded, not an infinity signal, a bounded signal, the output is also bounded. So that is called bounded input and bounded output stability. We will see more about this mathematical preliminaries required for control system in the next few videos. Thank you.